Hi, my name is Joonhyun Jeong from Neighbor Cloud and Keist. In this video, we're going to share our research work named as EResFD, Rediscovery of the Effectiveness of Standard Convolution for Lightweight Face Detection. This work explores an efficient face detection model that accurately detects face in real time on a CPU. So, today we are going to briefly talk about what the face detection task is and the motivation behind our work. Also, we are going to introduce some related works that dealt with our problem statement, and then we will introduce our proposed method with intuitive experimental results. Face detection task aims for detecting all the faces in the given image. It is fundamentally a preliminary step for various downstream tasks such as face authentication to verify the authenticated people. Also, it can also be used for face editing and face anti-spoofing task where the fake faces should be rejected. Since face detection is an initial step for the various downstream tasks, it requires running in real time while accurately localizing all the faces. For example, when constructing a pipeline of face recognition task, it can be decomposed into 3 steps, which firstly detect faces and its facial landmarks, warp the face, and get the facial feature from the recognition model. Since the subsequent models from face alignment and recognition are time-consuming, face detector should be executed within a short period of time. Also, the face detector should be accurate, since when the detector fails to detect face, the overall recognition fails. Therefore, in this work, we aim to develop a real-time CPU face detector while achieving high detection accuracy. Previous state-of-the-art real-time CPU face detectors heavily relied on depth-wise separable convolution layers for constructing computationally efficient model, which decompose standard convolution layer into 2 consecutive convolutional layers. Specifically, standard convolution kernels are decomposed into spatial-specific depth-wise kernels and channel-specific point-wise kernels. In this work, we rediscover that the actual inference speed of standard convolution is faster than the depth-wise separable convolution. In the below figures, we compared computational efficiency. In the left figure, depth-wise convolution exhibits much less flops than standard convolution. However, flops is not always matched with actual latency trend. Indeed, we observed that standard convolution shows faster inference latency than depth-wise convolution under extremely lightweight condition, where the number of channels is less than or equal to 16. Furthermore, we also analyzed the block-level latency behavior of standard convolution and depth-wise separable convolution. The results show that the standard conv block from ResNet is faster than depth-wise conv block from mobile nets. Motivated by the aforementioned observations, we propose an efficient backbone, EResNet, originating from ResNet. We redesigned ResNet for latency-efficient backbone and proposed several auxiliary modules such as SEP-FPN and CCPM for enhancing features to further improve face detection accuracy. We thoroughly analyzed the ResNet architecture and observed that the stem layers occupies a large amount over entire latency. ResNet stem layer consists of 7x7 convolution with stride of 2, so it requires a large amount of computation. To reduce the latency of stem layers, we first changed stride to 4 and also reduced kernel size from 7 to 5. To mitigate accuracy degradation, we introduced 2 additional standard convolution layers, effectively increasing the size of receptive field. Owing to these modifications, number of computations and latency is largely reduced. In modern backbone architecture, the number of channels is continuously doubled from the bottom to the top layer. This design trend is based on that high-level features are highly related to the specific classes. However, since there is only one object class in the face detection task, we assume that the channel dimension may be reduced. Therefore, we propose the channel preserving strategy, which does not double the channel dimension for every stage in the backbone network. In the right table, it shows that our strategy largely reduces latency and flops, about 66% of overall latency. To improve the detection performance for small objects, Feature Pyramid Network, FPN, is widely adopted. FPN propagates the context of high-level features from deep layers into low-level features from shallow layers. However, we assume that a significant disparity of receptive field size among the high and low-level features can lead to performance degradation when aggregated. To address this, we ensure that high-level features are aggregated solely with other high-level features, while low-level features are exclusively combined with other low-level ones, conveying consistent context. To further supplement the feature information, we also propose Cascade Context Prediction Module, CCPM, with a latency-aware module design. While the Context Prediction Module was originally proposed to enlarge the receptive field, our cascade design of CCPM aims for the same objective but promotes faster latency. For the experiments, we compared performance of various backbone networks. The result shows that standard convolution-based backbones, ResNet and EResNet, outperform depthwise-based ones such as mobile nets in terms of latency and accuracy. Also, our proposed EResNet achieves the best latency accuracy trade-off. Furthermore, we also compared with previous state-of-the-art face detectors. We note that our EResFD achieves a new state-of-the-art performance among the real-time CPU face detectors. Additionally, we further narrow the gap in accuracy performance compared to GPU-based detectors, while significantly reducing latency. We also conducted several ablation studies by comparing our proposed CEP-FPN with other FPN variants. Compared to the heavyweight FPN variants such as PANET and BiFPN, our CEP-FPN showed comparable or even higher accuracy while reducing 24% of latency. Also, compared to the lightweight FPN variants such as FPN and LFPN, our CEP-FPN showed much higher accuracy with similar latency. Also, we compared performance of our proposed CCPM module with the other feature-enhanced modules. We note that our CCPM achieves high accuracy while exhibiting the fastest inference speed. Finally, we compare our EResFD with RetinaFace, one standard lightweight face detector that conjointly detects face and facial landmarks. We note that our EResFD consistently achieves better performance on both face and facial landmark detection tasks. In conclusion, our work rediscovers the standard convolution for efficient face detection and redesign ResNet architecture to achieve better latency accuracy performance. We establish a new real-time CPU face detector, EResFD, achieving the state-of-the-art performance among the lightweight face detectors. This is the end of the presentation. Here are the QR codes containing web URLs for our research paper and our code implementation. Thank you for listening.